Welcome to Advanced Quantum Chemistry and my first lecture on electronic properties of molecules. So far we have only talked about the calculation of energies, ground state energies. They are of course important for determining, for example, the geometry of a molecule or the geometry of a transition state, and therefore describing chemical reactions which proceed on the ground state potential energy surface of a molecule. But there are many other properties of a molecule which are important to study and therefore to calculate, properties which are related, for example, to spectroscopy and therefore to the interaction with light or in general with electromagnetic radiation or the interaction between two molecules. Several of these properties correspond to measurable classical quantities, P, for which in quantum mechanics we can then define a quantum mechanical operator. And then we can calculate the expectation value of this operator with a wave function of the state of the system. You should remember, by the way, here that this expectation value calculated like this, if you want to compare that with the experiment, then this corresponds to the average of measurements made on many molecules which are in the same state. You might also want to remember that only if the state of the system, psi 0 here, is actually an eigenfunction of this operator, only in this case the expectation value will be equal to one of the eigenvalues of the operator P. In general, the state is typically an eigenstate of the Hamiltonian, and if the Hamiltonian does not commute with this operator P, then these functions will not be eigenfunction of P, and what we will get as an expectation value will be some average over the eigenvalues of P. Now, one of these operators, P, and one of these classical properties is, for example, the electric dipole moment. The electric dipole moment is a vector because it has a length or a value and a direction, so we can write it up with three components with respect to a Cartesian coordinate system. And if we have polar molecules, so that the positive charge of the nuclei and the negative charge of the electrons are not equally distributed, so we might have one end of the molecule where we have a small surplus of negative charge, and then another end of the molecule where we have a surplus of positive charge. These polar molecules have a permanent dipole moment. Now, the quantum mechanical operator, the electric dipole moment operator, has this form. It has a contribution from the nuclei here, where we sum over all the nuclei, and a contribution from the electrons. And both these contributions have exactly the same form. It's a sum over all the charged particles, and then it's the position vector of this particle, meaning the vector from the origin of the coordinate system to where the particle is, multiplied with the charge of the particle. So the electrons, of course, have minus the elementary charge, and the nuclei have the atomic number times the elementary charge. This is just a translation of the classical expression for a dipole moment to quantum mechanics. Classically, it actually would look the same. The only difference in quantum mechanics is now that these position vectors are now operators. So we can calculate the dipole moment, the permanent dipole moment of a molecule, by just taking the expectation value of this operator with the wave function of the state of the molecule in which it is. If the wave function we use here is obtained by solving the Schrödinger equation, so it's the exact wave function of our system, then the value we get for the dipole moment here, of course, is the exact value. How does one actually measure dipole moments in experience? Well, one puts on an electric field and then measures a change in some of the properties of a molecule, which depend on the interaction of the dipole moment with the electric field. Now, in quantum mechanics, we can also, of course, do that by adding an extra term to the Hamiltonian, which describes the interaction of the molecule with the field. And this term is written up here as a perturbation operator, as you can see, where E, the vector E here, is the electric field, and mu here is our electric dipole moment operator, which we had defined on the slide before. They're both vectors, so we have the scalar product, and there's a minus sign. There's a well-known theorem, the so-called Hellman-Feynman theorem, which relates to this situation. Feynman, that's of course Richard Feynman, the famous American physicist, whereas Hellman, that's Hans Hellman, who was a German quantum chemist. Now, the Hellman-Feynman theorem, which holds for exact wave function, and it also holds for all wave functions which are variationally optimized, meaning SCF, MCSCF, and full CI. So in the Hellman-Feynman theorem, one looks at the derivative of the energy of a system, the energy in the presence of, for example, but it has not be, for example, an electric field. So the energy in the presence of electric field, and one takes the derivative with respect to one of the components of that field. One actually can take derivatives with a lot of different parameters which are in the Hamiltonian, like for example the position of nuclei, a coordinate of a nucleus, which was the original case which was studied in the Hellman-Feynman theorem. But we can also apply it to the case of an electric field. So the Hellman-Feynman theorem says the derivative of the energy in the presence of a field with respect to one of the components of the field, evaluating this derivative afterwards for zero field strength, that is just the expectation value of the derivative, the corresponding derivative of the Hamiltonian with respect to the field. Now the derivative of the Hamiltonian we can easily evaluate. The normal Hamiltonian, as we had it so far, does not include the field. So the only term in the Hamiltonian which has a field, this is this extra interaction operator. And the derivative of this operator with respect to one component of the field, the alpha component to the field, which can be x or y or z, is of course then going to be the x component of the dipole moment operator and the minus sign. And this we have just seen on the slide before. That's nothing else than the component of the dipole moment. I mean, this is the expectation value of the component of the dipole moment operator. So this is the component of the permanent dipole moment. Which means that we actually, in addition to calculating a component of the dipole moment as an expectation value, we could easily also calculate it as a derivative of the energy in the presence of the electric field with respect to the corresponding component. So this gives us a second definition or a second way of calculating a component of the dipole moment as a derivative of the energy. And this will become very handy if we look at approximate methods, where we don't know the exact wave function, but we have an expression for the energy, where we can then calculate the dipole moment as this energy derivative. Now, as I said on this slide, that's the way how the electric field enters the Hamiltonian. So this is our perturbation operator, which we're going to use in here to the already. The Hellman-Feynman theorem is fulfilled for variational methods. That means it's fulfilled for Hartree-Fock, for Green-Charm DFT, for full CI, and for MCSF. Which means that there it doesn't really matter whether we calculate the dipole moment as the expectation value with our variational wave function, but this is going to be of course an approximation to the dipole moment, to the permanent dipole moment, because we're using an approximate wave function, or whether I calculate it as an energy derivative. Whereas for the non-variational methods like Mallet-Blessed perturbation theory or couple cluster theory, there is a difference between the two ways of calculating it. And the way which people normally prefer actually is the energy derivative way of calculating a dipole moment. Please note that in order to get the permanent dipole moment, we have to evaluate this derivative for zero electric field strength, and correspondingly here in the expectation value approach, we have to evaluate it with a wave function without the presence of the field. Now, what would happen if we actually look at the situation when the field is present? I had that before. Now, when an electric field acts on a molecule, it will pull the positive charges of the nuclei in one direction and the negative charges of the electrons in another direction. And this then will obviously lead to a change in the charge distribution of the molecule. And this change charge distribution also means that we will get a change in the dipole moment of the molecule. So the dipole moment in the presence of electric field here is of course the permanent dipole moment of the molecule if it has one, but then there's an extra contribution, a change in this dipole moment, which we call the induced dipole moment. And this induced dipole moment will also be there if there was no permanent dipole moment. So even non-polar molecules, in the presence of the electric field, there will be an induced dipole moment. Now we can write this dipole moment in the presence of the field also in terms of power series expansion. And I write it now here one component. So alpha is again either x or y or z. So it's one of the Cartesian components. And then the first term, of course, is the permanent dipole moment, or the corresponding component of the permanent dipole moment. And then we write it in a power series expansion of the electric fields. So here I have one component of the electric field, or I have to sum over all the three x, y, z components of the electric field. So this term is linear in the strength of the electric field, and the next term is going to be quadratic, and then it will be a cubic term. But for the purpose of this lecture, I stop after the linear term. And I have here a proportionality constant. And actually I don't have one proportionality constant, but basically I have 9 proportionality constants, because all the three components of the dipole moment, x, y, and z, can in principle be influenced differently by the different components of the electric field. So I have here 9 quantities which I can put together in a matrix. And this proportionality constant, which is how much the dipole moment changes linearly by the presence of a field, that's called the electric dipole polarizability. And it's called a polarizability tensor because it's a quantity with 9 components. And as you can see, I mean, from forever power series expansion, you can see I can define that as the derivative of the dipole moment in the presence of an electric field with respect to a component of the fields. And if I take here a diff, so if that's x and that's y, that's going to be the xy component of the polarizability. And in order to get rid of all the higher terms, the one which are quadratic or cubically dependent on the electric field, I have to evaluate this derivative afterwards at zero field strength again. So this is one component of the polarizability. If I remember now, so how does the energy expression where we originally defined the polarizability, so if they have large polarizabilities, I will get a large induced dipole moment. And that means if I put on an electric field, I will observe large changes in the charge distribution. That we had, as one of the ways of defining a dipole moment, we had defined it as the derivative of the energy of a molecule in the presence of the electric field with respect to the corresponding component of the electric field and that minus sign. Then one can derive or show that we can also alternatively define the polarizability as the second derivative of the energy now with 2 components of the electric field and still the minus sign, and we have to evaluate it at zero field strength. Now if I look now at the energy of the molecule in the presence of field and just write it up as a normal Taylor series expansion, where so the energy in the presence of the field, the first term is, if I do the Taylor series expansion around zero field strength, so the first term is the energy for zero field, meaning the energy without a field. That's the normal energy we have discussed so far. The next term in the Taylor series expansion is then the first derivative, and since the variable which we have is not just x, but it's actually a vector, it's the electric field with 3 components, so I get here 3 terms, so alpha can be x, y, and z. So I have the 3 derivatives of the energy in the presence of the field with respect to 3 components, evaluated, like always in the Taylor series expansion, at the expansion point, which was 0 field strength, multiplied with now the field strength. Then the next term is the second derivatives, 1/2, and sum of all second derivatives, and so forth. But these I know now. This is my component of the dipole moment, and the second derivatives are component of the polarizabilities. And don't forget the minus sign. So I can write this Taylor series expansion actually with respect to these properties here. So I get the energy of a molecule in the presence of the field is of course the energy without the field. And then I get a contribution from the dipole moment of my molecule times the electric field. And the next contribution is the square of the fields times the polarizability. So if I would know what the permanent dipole moment of my molecule is, and I would know what the polarizability of my molecule is, then I sort of could calculate at least the first two terms in the expansion of my energy of a molecule in the presence of an electric field. But I want to do something else. I want to use this in order to get expression for the polarizability. So what do we have? We have a molecule and we have an electric field. So we have a molecule perturbed by an electric field. So it's quite natural that we're going to use now perturbation theory. And what is the perturbation to second order look like in the presence of a perturbation? Here we had the expansion. Here linear in E, and here we have two components and multiplied by the polarizability. Well, we had that earlier. So we have our zeroth energy, that's the energy without a field. Then the first order correction, that's just the expectation value of our first order Hamiltonian with the unperturbed wave function. And the second order energy correction, that is this sum over states expression, where we have here the zeroth energy of the ground state and the zeroth energy of all the other states, unperturbed states, and we have these kind of transition moments with the zeroth order ground state wave function here and there, and with the other zeroth order wave functions and our first order Hamiltonians. Now if we insert the expression for our perturbation Hamiltonian, which is the scalar product of the dipole moment operator and the electric field, both here, which gives us that, and up here, then you hopefully already can see that this is actually the expectation value of the dipole moment operator in the unperturbed state. So that's just our dipole moment again. And here we have integrals with the dipole moment operator now with the unperturbed ground state and other unperturbed states. Now if we take the derivatives of this here, we can see that obviously we get back what we knew already, that we can calculate the dipole moment or component of the dipole moment as the expectation value of the dipole moment operator. But when we compare with the expansion here, so if we compare that with this expression here, here we'll get two components of the electric fields, which means that this thing here, that part of this sum here, that part must contain the components of our polarizability. And actually it does. So here we have an expression for the polarizability evaluated by perturbation theory. And the two comes because I have to take the second derivative, and there are two possibilities, so I get two terms by taking the second derivative. So here we have an expression for our component of the polarizability tensor as this sum over states expression from second order perturbation theory. Here we have the energies of the ground state, and this is then going to be the energy of all the excited states. And here we have integrals over the dipole moment operator from the ground state to the excited state, which are called transition dipole moments. And with these transition dipole moments, and actually with this energy difference down there is, that's the energy difference between the excited state of a molecule and the ground state, so that's what is called an excitation energy. It's actually the vertical excitation energy because they are evaluated both at the same geometry, at the geometry of the ground state. So with these transition dipole moments and that excitation energy, means it is actually just this part up here, because that, if I take the same component, that just gives me the norm squared. Jump back, you can see here in the numerator I had this norm squared of the transition dipole moments divided by the excitation energy. So if I replace this by the oscillator strength, as we can see, we can define a new property which is called the oscillator strength. So this is the transition dipole moment norm squared, which basically, so that's what I have here, the norm squared of this transition dipole moment multiplied with the excitation energy and then some constants. This property is called the oscillator strength. Or to be more precise, this is actually here one component, the x component of the oscillator strength. And if you want to get the whole x oscillator strength, you have to take sum the x plus the y plus the z component. So 3 times the same expression, just different components of the dipole moment operator here. Now, why do we want to look at the oscillator strength? Well, the reason for that is if you have a spectrum, for example, UV spectrum, but also could be IR spectrum, and you look at your peak and you integrate over your absorption peak, then you get what is called the integrated absorption coefficient. So this is just the integral over your extinction coefficient over the frequencies which belong to that absorption. And one can derive, and I don't want to do that, one can derive that this one is actually directly related to the oscillator strength. Yeah, to this oscillator strength. So the oscillator strength is actually the property which we can extract from the spectrum. It's the integral under, so it's the area under our absorption peak. Because, I mean, if you integrate here your extinction coefficient over the frequencies from your absorption, that just gives you the area underneath the top. So this is directly proportional. These are just some constants proportional to this oscillator strength. So the oscillator strength is what we directly get from a spectra, and we can calculate it here from the excitation energies and these dipole transition moments. And here, as I said, the total oscillator strength you get as the sum of the x, y, and z component. I have divided by 3. There's one interesting property for the oscillator strength, and there's one exercise where I have to prove that, because if you sum the oscillator strength over all the excitations in a molecule, meaning over all the excited states, n that's the excited state, over all the excited states, you can show that this is actually equal to the number of electrons. And this is a nice sort of check whether your calculation of the oscillator strength actually is good enough, because you know that if you would get the exact oscillator strength, it should give you the number of electrons. Now, since these oscillator strengths are defined as the norm square of the transition dipole moments times the excitation energy, I can also use, then the oscillator strength to rewrite my expression for the polarizability. Because the polarizability had also in the numerator, I get this expression here where I have the oscillator strength added and divided by 1/3, and now divided by the excitation energy squared. And I've written here the polarizability, what is called the so-called mean or isotropic polarizability, which is the average of the 3 diagonal components, so xx plus yy plus zz. That's called the isotropic or mean polarizability, which I've written here. So you can see, if either I have large oscillator strength or I have small excitation energy, in both cases, I will get a large contribution to the polarizability. And that means molecules which have low-lying electronic states, and therefore one or several small excitation energies, and molecules which have intense absorption, because if the absorption is intense, then the area under the absorption peak, of course, is going to be large, and I'm going to have a large oscillator strength. So molecules with low-lying states and intense absorption will have large polarizabilities. And if a molecule has a large polarizability,